All right, so I'm working on a different mic tonight, so I'm not sure you're going to be able to hear everything I say. I hope this comes out okay. Here's an example from section 7.3, number 8. And I'll first tell you that you know that you're going to be using the t-distribution because this is from section 7.3 where we learned what the t-distribution was, and it's a pretty interesting story, so if you didn't read it, everyone should read that. It talks about William Gosset, who was at Guinness Brewery, the beer making company, and he was trying to use statistics to make beer better. And I don't know anything about Guinness or beer in general, but I have heard that the Guinness company makes good beer, and it's interesting that they use statistics to do it. Anyway, apparently everyone uses statistics now, so that's kind of old news. But he was kind of innovative, and his pen name was Student T, I think is how it went, as how the story goes. And so this distribution is named after him. And here's what it says. It's right here. It says that you have the degrees of freedom you follow, and you've got area under the one tail or two tails, and so on. So anyways, we'll look at that more later. Okay, or there's the normal distribution that we used in section 7.3, but because we talked about the t-distribution here, it's kind of a giveaway. But on the test, you're not going to know that, right? So you gotta understand the difference. Now, what we learned in this section is that if it's from a sample, and if the other requirements are met, then we're going to use the t-distribution. So maybe we should review those requirements really fast. In the approved formulas, from the approved notes that you can have on the formulas and tables sheet, I like to scroll down or flip over to when they're discussing how to find p-values. That's going to come up for the next chapter, and how to word the final conclusion of a hypothesis test. Down below it says inferences about the mean, population mean mu, and choosing between t and normal distributions. We use the t-distribution when sigma, remember what that is? Well, you can go to the symbols page for that, which is also approved. Sigma, the population standard deviation, is not known, and the parent population is normally distributed. Or when sigma is not known and our sample size is greater than 30. If sigma is known, then you're in one of these two cases, in which case you're going to either have the parent population be normally distributed and use the normal distribution, or the sample size is going to be greater than 30 and you'll use the normal distribution. And if none of those things work out, then you're using either non-parametric or bootstrapping methods, things that we haven't talked about. So they wouldn't apply to this chapter. Okay, the other place I like to go is also part of the approved notes, and it takes that information about choosing between z and t, puts into a nice little table that I want to zoom in on here. Whoa, not that much. Where it says the same thing. Basically, either you know sigma or you don't know sigma. Well, if we know sigma, then we're most likely going to be using a normal distribution. Okay, so if sigma is known and the parent population is normally distributed, use z, which is the normal distribution. Known and sample size greater than 30, use z, normal distribution. Sigma unknown, we're going to use t. Okay, so let's go back to this problem. We have a sample set here, which we can find the sample standard deviation, which is s, but does it mention anywhere in here what sigma is, the population standard deviation? You can pause the video and watch, but no, it doesn't. So that indicates to me, since I'm finding a confidence interval around the mean, and I don't have the population standard deviation sigma, I'm going to have to use t. So go ahead and take my set here, my sample. Now this one's interesting because my sample size is definitely not greater than 30, right? And so I really seem at a loss to use either of these, right? Because it says Sigma's unknown, sigma's unknown. I'm in one of these two bullets right here. Is the parent population normally distributed? I don't know. I'll go back and read for that, but I do know that the sample size is not greater than 30 since it's 7. So I really shouldn't be using these unless I know the parent population is normally distributed. I should be using something else, right, that I don't have right now. Well, since I don't have it right now, and apparently they're waiting for an answer, I've got to assume that I'm just going to go forward with it. But when I read, the population is about sample of 7 cars tested with nitrogen oxide emissions. I guess that this population set must be normally distributed because it's going to allow me to go forward here. Alright, so if I'm using StatCrunch, I'll go ahead and just have it whip the whole thing out. Go down to Stat, T-Stats, one sample with the data, because I actually have it. State where it is, and then choose a confidence interval instead of a hypothesis test. We'll use that for chapter 8. The process is pretty much the same in terms of the mechanics of using the technology. I want a 98% confidence interval. I'll go ahead and store this right back into my set, hit compute. So this should be my lower limit and this should be my upper limit. Now what's all this other stuff, this standard error and this degree of freedom and the sample mean? Well, it took the data, calculated the summary statistics. Which summary statistics would it need? Think about that. We'll go find out right now. If you're in chapter 7, sorry, it's all the way up here. What you're going to need what you're going to need to create your confidence interval about the mean, which is right here, are one of these two things. Here we need the critical value. I'll zoom in a little bit. The critical t value. Alpha is the level of significance, and now that is the complement of your confidence level. So if our confidence level on this problem, which it is 98%, then we have a 2% significance level. And then split that in half makes 1% for each tail, the left and the right tail. But when I go look up in the table, I don't have to delineate between left and right tail. I just have to say, am I looking at the area under 2 tails or under a single tail? And let me show you how I would do that. I'm going to make this go a little faster. Let me go to my t. Here's my t distribution. You could have also just clicked on it straight from the homework. Okay, if I am using a confidence level of 98%, that means the middle is supposed to be 98%, then I have 1% in a single tail, whether you're looking at the left or the right, and we would be looking at the right, the area to the right of that critical value we're looking for. But if I was looking at under 2 tails, it would be 2%, right? Because 100 minus 98%. So I would look right here, 1%, come down to degrees of freedom of 6, because I had 7 items in my sample, and I'd be using 3.143. So that would be my critical value with a 1% area to the right. And I would plug that in right here for that number. Then I would take the sample standard deviation, which I didn't need to show, but I could have shown. Divide that by the square root of 7. And then this is my standardized score, right? So this is my maximum margin of error. I subtract the maximum margin of error from the mean, I add the maximum margin of error from the mean, and I create this net. And now we don't know if the mean, population mean, mu, if it's actually in that net. We just know that we threw this mathematical net out there, this interval, from one point to another point, and we're saying we're 98% confident that it's in there. So like 98 out of 100 times when we create a confidence interval, it would be in there. or those intervals, 98 out of 100 of those intervals would wrap around it. So that's the mean that I used, and I did my standard maximum margin of error on both sides, and I got these values, which rounded to 3 decimals, and that is what we want to do for t-score, for student t-distribution questions. You would get 103 thousandths and 203 thousandths when you round that. All right, so let me see the errors that I have here. We put 0.92, 92 thousandths, and 18 hundredths. I'm going to make a guess and assume that we use the wrong distribution. So let's say we use the z-stats, one sample with data, run it. Check all our pieces here. Oh, interesting. So if you did this, of course, since you're using a z-distribution, you would have assumed that you knew that whatever the population standard deviation is, and I don't know it. So what would you have put there? I'm going to guess that you put that number. You know, where it gave you that emissions minimum, that benchmark number. Let's see what happens if you run that. Nope. That doesn't give me those boundaries you had typed in. So let me actually run StatCrunch has been acting up, hasn't it? Let me go ahead and run the summer statistics. Really all I need here is the variance. I'm sorry, the standard deviation. Okay, so if I use this with the wrong distribution, just pasting it in there. I get a boundary of 118 thousandths and 186, not closer. Man, sometimes I can recreate the mistake and I can then help further explain what not to do, or you know, where your error was, but I don't know what you did here, so you'll have to probably just write it out and explain it to me, and then I'll try to clarify. I guess one last thing I can try is, did you do a t-distribution, student t-distribution? Did you do one sample with data like we wanted, and then, sorry, if you are having StatCrunch glitch for you like it is for me here, I have learned a trick. If you click into one of these other cells and then run it, it shouldn't bounce out of the window like it's been doing. And allow you to go through with it. Okay, oh, what I was going to change is, okay, so if this distribution currently is from 103 to 203, and yours is 900ths to 1800ths, skinnier, smaller, then maybe what you did is you chose a, let's see, what would that be? A smaller percentage. So maybe you didn't put in 98, but you put in something like, if you subtracted, maybe you put in 96. Or maybe you left the default, which is 95. Maybe I should try that next. So if I put in 96, nope, I think you may have just left the default. Okay, so if you didn't change it to the correct confidence level, no. I mean, that did bring it together a little bit, but all right, the second part of the question, since I've gone on too long trying to figure out what that was, can we safely conclude the requirement that nitrogen oxide emissions be less than 165 thousandths, that they're going to be met? In other words, if that's the true population proportion, are we within the range of the interval? And our confidence interval wraps around that and wraps it around it very well. There's a very good overlap. So no, it is possible that the requirement is being met, but it is also very possible that the mean is not less than 165 thousandths grams per mile or whatever that is. Right, so I'll go with that because we are 98% confident that the average falls between that, but that interval overlaps this less than 165 thousandths benchmark. So that piece that falls to the right of this, which very well could contain the population average, would be above that minimum, since it's a minimum. What we would like to have happen, let me put it this way, is that this whole entire interval would have fallen below this benchmark. Then we could have safely said, that, it would have been, that we could expect that it would have been less. So anyway, I hope that helps. Probably shouldn't be making videos at 1:28 a.m., but that's the time I have. So I hope you enjoy this. It's gone on much too long, and yet I still go on.